Okay, this video is about dot products, and we're also in the process of talking about dot products, going to talk about the angle between two vectors. How would you find the angle between two vectors if you have other information about those vectors? Notice I didn't specify what other information we have about those vectors. That will come into play in a minute. Okay, so what is a dot product? Um, Now, a dot product, it's a very tricky thing to explain, but the way that I think I've settled on is like the best way to explain it is it can be thought of as the influence that one vector has on another. Let me give you an example. Now, this picture may or may not incite some PTSD, especially if you have older siblings who just destroyed you in Mario Kart growing up. But we all have probably experienced this. You're playing Mario Kart or any other game that has a little boost pad. And if you hit that boost pad like dead on, so let me actually draw some vectors on Toad here. Okay, so let's say this is Toad's speed velocity vector, right? He's heading off that direction. But the boost is kind of going this direction, right? The more aligned those two arrows are, the more impactful that boost is. So if you hit that boost dead on, it gives you a better boost. If you hit it like completely sideways, right? It doesn't give you a very good boost at all. So a dot product kind of is a measure of how impactful that boost is to your overall, like to how impactful the boost vector is um, to your initial velocity vector. And it seems like a funny way of describing what a dot product is, but you can imagine there might be real world applications. Well, there are, obviously, that's why it's a thing. But there's real world applications for dot product. It has to do with all kinds of things like energy production, um, some collisions, all kinds of things. And certainly dot products themselves are important for just purely mathematical reasons, into vector calc especially. But let me show you another weird thing here about dot product. Now, computing a dot product, honestly, it's extremely simple. It could not be a more simple process. So one of the ways we multiply vectors is by a dot product. And basically all you do is you multiply the horizontal components of two vectors, you multiply the vertical components of two vectors, and you add those two products together. So for example, if I had these two vectors, vector v and vector w, and I've given their x and y components. Now remember, I could also say that this is just 3 I hats, that vector v is equal to 3 I hat plus 4j hat, or vector w is equal to negative 5 I hat plus 6j hat. You could totally write it that way too. It's still the same way. In that way you would just multiply the I hats and multiply the j hats and then add them together. Okay, but in this case, essentially all this would be is 3 times 5, right? So 3 times 5 is just 15. Let's skip that step. Plus, 3 times negative 5. Sorry, 3 times negative 5, that's negative 15. Plus 4 times 6, 24. So the dot product of vector v and vector w in this case is just 9. Now, hey, 9, cool, super simple math. But how does that make any sense? You multiply two vectors together, and vectors are things that have two pieces of information, a magnitude and a direction, or in these cases, a horizontal and vertical component. You multiply them together and you just get 9. Like, how does that make sense? 9 is a scalar value, vectors are vector values. It seems very odd to me. And so that's why you kind of need some context here. If the process we just used to find those vectors reminds you of anything else you might have done in math, namely something like the determinant of matrices, well, you're not far off there. They're very related. In fact, when you get into vector calculus, determinants of matrices and dot products are used all the time, and they're very similar. So well, they're not the same thing, but they're similar. Okay. So one of the reasons we might need to use a dot product is to find the angle between two vectors. Now, these are not vectors here. These are just two lines in space, and they have the endpoints shown there. And we want to know, is there a way that we can calculate that angle alpha? And there is, and the way is the law of cosines, which are written there below. Now, in order to do this, we kind of have to say, or we have to imagine that there's another line here. Okay, it completes this triangle, right? And this side length over here, opposite the angle alpha, is like side length lowercase a. Okay, and then opposite angle b is side length b, lowercase b. We usually use. Okay, and then opposite opposite angle C is side length C. Okay, and then the law of cosines will let you find that angle. Now, at the end of this, you have A, B, and C in this particular example, and we're trying to find alpha. We're trying to find the angle between these two lines. You would have to use something called inverse trigonometry. Now, this also applies to vectors. Okay, look, now instead of that triangle, now we just have these vectors. I said vector v, vector w, and then this would be vector v minus w. Okay, if that's confusing, the reason, and remember when we talked about the adding vectors, if you took this vector w and you put it over here and you made it negative, so if I made vector, well, sorry, I messed that up. Let's see if we can undo that. If we made vector w negative, so it was like over here, and the arrow would be going the other direction, right? Then this vector is vector v minus w, right? So that's vector v, that's plus a negative vector w, so v minus vector w. In any case, let me undo all that. So all we do here is we substitute in. So for A, instead of side length A, it's vector v minus vector w. Okay, instead of side length B, it's vector w, right, etc. Now you can say, all right, if I have this magnitude of these vectors squared, magnitude of this vector squared, well, that's the side length, right? Okay, it's the side length magnitude. That's just a dot product. It's that vector times itself, that vector times itself, that vector times itself. You'll have to trust me that at the end of this, I'm not going to go through all the steps, but I mean, you apply some properties that apply to vectors and dot products. You end up with this equation here. The cosine of the angle between the two vectors is equal to the dot product of those two vectors divided by the product of the magnitude of those two vectors. It looks confusing, and that's because it is. This is not intuitive. It comes from the law of cosines, which itself, if you've ever sat through the proof of the law of cosines, is honestly, it's pretty nice. It's not super difficult to understand where these things come from. However, it's more work than is necessary. Here's an example where we could feasibly use, and we do use the dot product to find the angle between these two vectors. We're given the information, all the information we need about vector v and vector w. Okay, they're horizontal vertical components. So what we would need to do then is calculate the magnitude of vector v and vector w. So I'll tell you right away that the magnitude of vector v is 5, because that would be a 3, 4, 5 right triangle. The magnitude of vector w is 17, because that would be an 8, 15, 17 right triangle, right? I just squared both, it just used the Pythagorean theorem, right? We have this triangle here, that's a 3, that's a 4. Pythagorean theorem gives us 5. Same thing for the other one. So we have the magnitude. The dot product would be really easy. The dot product of v dot w would just be 45 plus 32, which is 77. No, it's 87. So here we go. We have 87 is equal to 5 times 17, which is 85. And then times the cosine of angle alpha, now, or angle theta in this case. Now, all we would have to do is divide both sides by 85, and we'd have the cosine of theta. Oh, sorry, I can't write. The cosine of theta is equal to 87 divided by 85. I must have messed something up here. I'm sorry. Let me redo this. This is 77. 77. It is 77, not 87. I don't know what I'm doing. Okay, 77. All right. So cosine of this is very, very hard to read, but the cosine of theta is equal to 77/85. So that doesn't really help us because it doesn't give us theta. So what we need, the extra piece of information we need here, is how to use inverse trigonometry. Now, if you've never used inverse trigonometry before, it couldn't be simpler. Normal trigonometric functions, the input to normal trigonometric functions are angles. Okay, you plug in an angle, you get out a ratio of side lengths. On the other hand, inverse trig functions, you input a ratio of side lengths and you get an angle out. Now, these are really easy to do if you have common side lengths. So if you have, for example, right, the inverse sine of 1/2 tells you, okay, the sine of what angle is 1/2? 30 degrees. So you can basically do those in your head, and we'll talk a lot more about how to do inverse sine stuff kind of by hand. But your calculator, because in the normal world, you're not always going to just have these nice numbers. So your calculator has buttons for inverse trig. And now, depending on if you're in radians or degrees, you'll want to make sure you're in the right units. But if we wanted to find, for example, the inverse cosine of 77/85, we could do that, and we would get 25.05 degrees. Okay, so that is the angle between those two vectors. Let's get a little bit more practice on that. That is using inverse trig, okay? And just do some really simple versions of those problems, okay? So here's a triangle, it's a right triangle. We have theta right here. We have the opposite side and the adjacent side. So the inverse tangent of 6/14 is 23.2 degrees, okay? And again, just to show you that that's how that works, you get second inverse tangent of, let's say, what was it, 6/14. 6/14. Sorry, I kind of got off. It's 23.2 degrees. Okay, and you can go through and you can get any values like this. It's no problem. If you had this, now it depends what side lengths you have, right? For this, with respect to this angle theta, we have the adjacent side and the hypotenuse. So the trig function that involves adjacents and hypoteni, is cosine. So we would use inverse cosine of 420 divided by 1172, and we get 69. Okay, so maybe this begs the question for you, is why do we need that other formula for dot? Why do we need that dot product formula when we have the ability to use inverse trig? That's the argument I'm making here for you, because for our purposes in this class, we don't really need to use the dot product extensively. We might as well use a much more intuitive approach that I kind of hinted at earlier. Because if I just have this, if I break this vector down into its horizontal and vertical components, which were 3 and 4, and this was 5, and this bigger one down into its horizontal and vertical components, so in this case 15 and 8, well, now I have this angle, like let's call this angle alpha, and this angle beta, right? This bigger angle is beta, and this smaller angle is alpha. Well, isn't it the case that theta would equal beta minus alpha? Why would I have to do this dot product stuff? Couldn't I just say that this angle theta is equal to the inverse tangent or arctangent of beta, which was 4/3, minus the inverse tangent of this alpha, which was 8/15? Like, this would literally give me the answer of the angle between these two vectors, rather than having to go through the dot product property. So what we're going to do in the next video and in section 5.5 of the book is all about finding, well, part of it is using this idea of finding the angle, these special angles, to solve novel problems. And the kinds of problems we're going to come across are things like there is a car on a hill and it's going to roll down the hill unless the brakes are applied. What would be the force you'd have to apply the brakes? What force do the brakes have to apply in order to prevent the car from moving? Or maybe you're pulling a wagon at an angle of 45 degrees with the horizontal. What's the effect of your pulling on the motion of the car of the wagon? And then the big one, the one that throws students for a loop, but I promise you is not any more difficult than just drawing big right triangles and interpreting the problem, are airplane problems. So you have an airplane, it's flying, the wind is blowing like out of a different direction, and it's going to blow you off course, or you have to like correct your course to accommodate for the wind. What are the angles involved there? And that's it. Like that is what the dot product will accomplish for us in this class.